Good morning, children. Today we are going to start chapter number 1, number systems. You are already familiar of many number systems like the one natural numbers. When we start counting like this 1, 2, 3 and so on. So this is the set of numbers denoted by capital N, whose smallest member is 1, and we write the numbers like this 1, 2, 3, 4 and so on, because there are infinite numbers in this set. So this set of numbers is known as natural numbers. Now if to this set I just add 0, then I get the next set of numbers, and this set of numbers denoted by capital W is known as whole numbers. So here 0 is the smallest whole number, and largest whole number we cannot find because there are infinite numbers in this set. Same is the case with natural numbers. I know that the smallest natural number is 1, but I can't find the largest natural number as there are infinite numbers in these sets. So natural numbers, whole numbers. Now what I do if I add negative numbers also to this set, like say because on the left side we have infinite numbers on the number line, so I can write dots, I can put dots, and then I can start writing like this: -3, -2, -1, 0, 1, 2 and so on. It means in this set, on both the sides, left as well as right side, we have infinite numbers. This set of numbers is called the set of integers. Now children, the next set of numbers are known as rational numbers. You have done in your previous classes that a rational number is a number which can be expressed in the form of P by Q, where P and Q are integers, and these are the conditions, means P and Q are integers and Q should not be equal to 0. So I repeat, a number is said to be a rational number if we can express it in the form of P by Q, where P and Q should be integers and Q should not be equal to 0. So like 3 by 5 for example, and 7 by 9, even I can take -3 by 12, 0 by 1. So here 0 by 1 is 0, which is again a rational number. So any number which we can put in this form is known as a rational number. Now children, there is another set of numbers which you are not familiar with, which are known as irrational numbers. This set is new for you people, irrational numbers. If we are not able to express the number in this form, for example, I have √2. √2 can be written as √2 by 1. Here Q is not 0, that is 1 is not equal to 0, but this condition is not getting satisfied. According to the definition of rational numbers, P and Q should be integers. Here √2 is not an integer, therefore √2 is an irrational number. Other irrational numbers are, I can give you more examples like √3, √5. But if I take √4, then we know that it is a perfect square root of a perfect square. So the answer is 2, which is a rational number. Right? If we take both rationals and irrationals together, then we get a new set of numbers known as real numbers. It means whether they are natural numbers, whole numbers, integers, rationals as well as irrationals. All these numbers are contained in the set of real numbers. And each of the real number can be represented on the number line So that is why the number line is known as real number line. Children, this rational number, it contains all the sets in it. Like every natural number is a rational number. Every whole number is a rational number. Similarly, every integer is also a rational number. But the converse is not true. Like if I have a rational number, say 5 by 3. So if the question comes like this, that is every rational number a whole number? Then the statement is false. We can give a contradictory example. Like we can take like 5 by 3 is a rational number which is not a whole number. Similarly, children, all natural numbers are whole numbers, but all whole numbers are not naturals. Actually, when true-false comes in your exam, you have to justify them also. So, you have to give proper reasons. Like, if the question is every whole number a natural number? Then you will say, no, every whole number is not a natural number, as we have an example that 0 is a whole number which is not a natural number. Children, in class 7, you have done this topic, that is to find a rational number between two given rational numbers, right? Or between two integers also we can find, to find a rational number. So, let me take an example. Find three rational numbers between 1 by 7 and 2 by 7. So, a very easy method I would like to take. First step in this will be, what we are going to do, multiply the numerator and denominator both the numbers by 10. So if I do 1 by 7, numerator multiply by 10, denominator also multiply by 10. And the second number is 2 by 7, multiply the numerator and the denominator by 10. I got here 10 by 70 and here I got 20 by 70. Now children, these are the boundaries. We have been asked three numbers. Like from 10 by 70, the next number I can take 11 by 70. Then I can take 12 by 70, 13 by 70 and so on. 14 by 70, 15 by 70 and till 19 by 70 I can take any three numbers of my choice. So this is the first method which is very easy. Why I am multiplying by 10? Because it is the number which is very easy to deal with. If we want more numbers, suppose I want more than 10 numbers, I can take the multiples of 10. So I can multiply by 100, I can multiply by 20 or any other number. Any convenient number I can choose. But the thing is that I have to multiply both numerator as well as denominator by the same number. And then I'll get these numbers in between. I can also take 19 by 20. This is the last one. 19 by 70. For finding these numbers, you have another method in which if A and B are two rational numbers, then to get another number between them, just add them and divide them by 2. This is method number 2. But in this method, what happens that we have to take LCM a number of times. That is why it becomes tedious. But if you want, you can use this method also. Just add the numbers and divide them by 2. Now students, let us talk about the decimal expansions of the rational numbers. If I have a rational number, say 3 by 4. All of you know the division process. So simply by dividing 3 by 4, I can convert it into a decimal. Obviously, I need to take a decimal first of all. So I got a 0. 4 into 7, 28. Now 2 is left. I have to borrow a 0 because I have already taken a decimal. 4 into 5, 20. So the remainder is 0. Now this method is simple division by which I can convert a rational number into a decimal. By simply dividing, I can convert a rational number into a decimal. If you observe it, this type of decimal is known as a terminating decimal. Why? Because I have got the remainder 0. I have got the remainder 0. If I take another example, if I take 1 by 5, then the decimal expansion of 1 by 5 is 0.2, which is again terminating decimal expansion. Such decimal expansions are known as terminating decimal expansions. Because the division process stops, we get 0 after a finite number of steps. That is why such decimal expansions are known as terminating decimal expansions. Let us take another example. Now let us divide 1 by 3. Let us start the division process. 1 is the dividend, 3 is the divisor. I have to take a decimal and then a 0 will come because 1 was smaller than 3. Now I will multiply by 3. So I will get 9 here. Again the remainder is 1. So let me take another 0. 3 multiplied by 3 I'll get 9 here. Again remainder 1. Then again I'll take one more 0. Again by 3. You can observe that this process will continue forever. It means I'll keep repeating the digits and will never get the remainder 0. In this case, the decimal expansion I can write like this: 0.333 and so on. So such a decimal expansion is known as a non-terminating decimal expansion. I can also write it like this: 0.3 bar. This type of decimal expansion is known as non-terminating decimal expansion. So basically, if we get 0 remainder, such decimal expansions are terminating, and if we do not get the remainder 0, then such decimal expansions are known as non-terminating decimal expansions. Now let me take another example. If I have number √2, if I take √2, we can find its value by long division method. So you will observe that you can try long division and you will get 1.41421356 and so on. In this case also, the decimal expansion is non-terminating, but we can see that we don't get the digits with bar. It means the digits are not repeating themselves. So this type of decimal expansion is known as non-terminating and non-repeating. Now let us consider these decimal expansions once again. Basically, it is of two types: terminating and non-terminating. If we get remainder 0, okay, if we get remainder 0, it's terminating. And if remainder is not equal to 0, then it is a non-terminating decimal expansion. Now, non-terminating again has two cases where the digits repeat themselves, then it is repeating, and if the digits do not repeat themselves, then this type of decimal expansion is known as non-repeating, non-terminating and non-repeating decimal expansion. Children, whenever we have the number has a terminating decimal expansion and remainder 0, such numbers are always rational numbers. It means we have got another definition for rational numbers, that is, if the decimal expansion of a number is terminating, then they are rational. Even if the decimal expansion is non-terminating but repeating. In this case also the number is a rational number. But the third case, when the decimal expansion is non-terminating and non-repeating, then such numbers are known as irrational numbers. So according to the decimal expansions, we have got another definition for rationals and irrationals. If the decimal expansion of a number is terminating or non-terminating but repeating, then in both the cases it's a rational number. But if the decimal expansion is non-terminating and non-repeating, like that of root 2, root 3, pi, then such numbers are known as irrational numbers. Now children, by simply dividing, we have seen that if I divide 3 by 4, by long division I can convert it into a decimal like 0.75. Converse process is to express any decimal in the p by q form. P by q form means here this form 3 by 4, where p and q should be integers and q should not be equal to 0. So if I take this example, say let us take this decimal 0.75. What you will do, you will simply remove the decimal by writing 75 upon 100. So, and then you can convert it into lowest form, which is 3 by 4. Similarly, if I take one more example, it is 0.029 and I have to express it in the form of p by q. I can simply remove the decimals like 29 divided by 1, 2, 3. So there will be 3 zeros in the denominator. And already it is in the simplest form. So this is the p by q form for this decimal. Now, suppose I have a rational number like this, 0.3 bar. We have done that both these categories, like if it is a terminating decimal, then also it's a rational number, and non-terminating repeating decimals are also rational numbers. That is why we have a method to express such non-terminating and repeating decimals to express in the form of p by q. So let us first of all solve this example 0.3 bar. The first step here will be, you have to take it as let x is equal to 0.33. Just remove the bar and put the dots. This is my equation number 1. Now children, we have to multiply both sides by 10. Why 10? Because the bar is only on one digit. So let us multiply both sides by 10. I got 10x is equal to 3.333 and so on. This is my equation number 2. Now what I am supposed to do? Subtract equation 1 from equation 2. You will write the statement here. Subtract equation 1 from equation 2. Then what you will get? 10x minus x is equal to 3.333 minus 0.333 and so on. So left side I got 9x and on the right side 3.000. So simply I can write it as 3. Let me explain this difference, how I have taken. See, if I take 3.333 with dots and I subtract from it 0.333, you will find that all these digits after decimal, they will become 0. So even if I have 3.000 infinite times, it is same as 3. That is why here the answer is 3. Now just shift this 9 to right hand side. So 3 by 9, which is in the lowest form, 1 by 3. So we have expressed 0.3 bar as 1 by 3. Now children, let's take the second example, that is 1.27 bar. You can see that bar is on 2 and 7 both. So let us repeat the first step. Let x is equal to 1.2727 and so on. This is my equation number 1. Because bar is on 2 digits. So in this case, we have to multiply the both sides by 100. If suppose bar is on 3 digits, I will multiply both the sides by 1000. So in this case, as the bar is on 2 digits, so I will multiply both sides by 100. So 100x is, if you multiply it by 100, you get 127 because decimal will be shifted right side 2 places. 127.2727 and so on. These dots are showing that this is non-terminating repeating decimal. Now again the same process, we have to subtract equation 1 from equation number 2. So subtracting equation 1 from equation 2, I will get 127.27 dots. You have to put the dots in each step because it's non-terminating repeating decimal. Now 100x minus x is 99x, and here same thing will happen. After decimal we have 272727. Here also after decimal I have the digits 272727. So on subtracting, I will get 126.000, which is not necessary to mention. So 126.000 is same as 126. Now children, in the next step, I will shift this 99 to right hand side, 126 upon 99, and ensure that children that this should be in the lowest form. So by cancellation, bring it to the lowest form, which is 14 upon 11. So this is the answer. I have expressed 1.27 bar as P by Q. And again, let me remind you, here P and Q should be integers and Q should not be equal to 0. Let us take another. Here the number is 0.235 bar. You can observe that bar is only on 2 digits, that is 3 and 5. So for our convenience, what we can do, first we can multiply this number by, first of all let us take it x. Okay, let x is 0.23535 and so on. Observe that 2 is not repeating. Only these 2 digits 3, 5 are repeating. Now this is my equation number 1. Let us shift this digit which is not repeating to the left side. So for this, first multiply equation number 1 by 10. So I got 10x is equal to 2.3535 like this. This is equation number 2. Now because bar is on 2 digits, now again multiply equation number 2 by 100. Okay, because bar is on 2 digits, we will multiply this equation by 100. On multiplying by 100, the LHS will become 1000x and the RHS will become 235.35 and so on dots. This is my equation number 3. Now see in equation number 2 also, after decimal I have 353535. Here also in equation number 3, after decimal 353535. Now we have to subtract equation number 2 from equation number 3. So let us subtract equation number 2 from equation number 3. That is 1000x minus 10x is 235.35 dots minus 2.3535 and so on. Now when you subtract this, on the left hand side I will get 990x, and on the right side I will simply get 233 because 5 minus 2 is 3 and this 23 as it is. In the next step, take this 990 to the right hand side. Now children, we have to express it in its lowest form, but as we know that it is already in the lowest form, so this is the final answer. Now children, let us take the last topic of today's class. We have just learned how to find a rational number between two given numbers. But now I will explain that how to find an irrational number between two rational numbers. For example, this is the example 10 of your book. Find an irrational number between 1 by 7 and 2 by 7. It is a very easy method. What you are going to do, we need the decimal expansions of these. In the step 1, write down their decimal expansions. And you can just find till 2 places after decimal, that is sufficient. Like 0.14, and you can put dots after that because we need only the first 2 digits. Then similarly 2 by 7 is 0.28 and so on. I just want these digits because I want to get an idea that the number which I am going to find, it should lie between 0.14 and 0.28. As we all know now that the irrational number is a number which is a non-terminating and non-repeating decimal. Therefore, an irrational number between them is an irrational number between 1 by 7 and 2 by 7. Directly I can write like this. See, this is the range 1, 4. So I can take 1, 5. I can start with 1, 5 or 1, 6. But I cannot take 1, 3. So that is why this expansion is needed. So now we don't have to exceed this limit 2.8. I can take 0.27 but not 2.8. Then see the process. What I can do, I will write 1501, then 001, then 0001 and put the dots after that. Now you can see children that this is a non-terminating and non-repeating decimal expansion. As we are increasing 1 0 at each step, this is ensuring that the digits can't repeat themselves. So this is how directly we can write the irrational number between two rational numbers. Let me give you an example of one more such number. So between these two limits, I can choose another number like 0.27. Then I can take 0, 5, 005, 0005 and so on. So these are two irrational numbers between these numbers 1 by 7 and 2 by 7. So children, in today's class we have covered so far different number systems, their decimal expansions of the rational number, and the converse process, that is to express a rational number in the p by q form where p and q are integers and q is not equal to 0. And we have learned how to find the rationals as well as irrational numbers between two rational numbers. Now based upon this, I'll be sending you the introductory notes on the group and also the work which is to be done in the notebook. Thank you so much for today.